Hello and welcome to JHEP's lesson on calculations using Kc. This should be suitable for OCR and for all other examples as well. What we're going to do, we're just going to go through two example exam questions in order to figure out how to actually find out Kc from equilibrium data. So over here we've got syngas, and that's a mixture of carbon monoxide and hydrogen gases, and this is the equation below. An equilibrium was set up and between those three elements, those three compounds, in a 2.0 decimeter cubed sealed vessel. First thing I would do is to highlight the elements and the most important details. This over here, I can tell you now, is not relevant to any of the question, so we don't need to worry about that. And this is the equilibrium shown below. Again, I would highlight the two here because we need to remember that this is 2 moles of hydrogen gas, and these are all one relative to the carbon monoxide and the methanol. So we've got these components and we've got the number of moles at equilibrium. So at equilibrium we can see that 6.2 times 10 to the minus 3 moles of carbon monoxide gas was present at equilibrium. So the first question is, state two features of a system that is dynamic equilibrium. Well, the first one, which you just should know, is that the rate of the forward reaction is equal to the rate of the reverse. And okay, remember dynamic. And the second one is that the concentration of the reagents and the products are constant. They're not the same, they're not equal, they're constant, and they constantly interchange between each other as well. Okay, it is important not to say that the concentrations of the products and the reagents are equal, because then Kc would then equal 1. So we can't, so it most likely will not be equal. So that will give you your 2 marks over here. The second one, write an expression for Kc in this equilibrium system. Well, this, it says for this equilibrium system, so it is not, it is too vague to say Kc equals the concentration of the products over the concentration of the reagents. Okay, over the course of F325 chemistry, you would probably realize that products comes before reagents. Like for example, when we need to find the sum of the entropy change, is always the sum of the entropy of products minus the sum of the entropy of reagents. It's always usually products minus reagents or products over reagents. So that's a good way to remember it. So over here, for this equilibrium system, it needs to be Kc equals whatever the products is, which is methanol. So that would be CH3OH. And we need to check that there is no number in front of it. If there is a number in front of it, that would automatically become the order, but it is not, so we can keep it like that. And over here we have the concentrations of the reagents, which is CO and H2. Now you need to be careful to not mistake H2 to look like this. Okay, that is wrong, because this is a superscript, well, a subscript should I say, and that is one whole diatomic molecule, so that needs to be over here and not at the top. But seeing as we've got 2 molecules of H2, we need to put the 2 up there as well. So that is the expression for Kc. Again, expression, okay, don't worry about that, I'm not going to go into that much details. Now for Kc, for this equilibrium, we need to remember that to calculate it, it needs to be the concentration of methanol over the concentration of carbon monoxide and hydrogen gas. We've only got the moles over here. We've only got M when we need C, which is concentration, by the way, and that's moles. So what do? We look back at our question and we see that we've got the volume here. So we've got the number of moles and we've got the volume, and we need to find the concentration. If we remember F321 or Unit 1 Chemistry, AS Chemistry, we should be able to manipulate this to find the concentration. So it would look like the number of moles divided by volume, which will give us our concentration, okay? Because N equals C times V, and if we rearrange that, it will make that. So let's have a look. 6.20 times 10 to the minus 3 divided by 2, because it is already in decimeters cubed. Again, that's another thing you need to look out for, whether this is in centimeters cubed or decimeters cubed. So seeing as this is in decimeters cubed, we can do 6.20, let me use a different coloured pen, 6.2 times 10 to the minus 3 divided by 2. So that will give us our answer of 3.1. Well, okay, let's put the 0. Let's be accurate. 3.10 times 10 to the minus 3 moles per decimeter cubed, to the minus 3 anyway. Now let's do it for the other two. We've got H2 there, so it would be 4.8 times 10 times 10 to the minus 2 divided by 2 to give us 2.4 times 10 to the minus 2 moles per decimeter cubed. Now for methanol, it would be 5.2 times 10 to the minus 5, I believe, divided by 2. Let me just check. Let me just double check. Yep. Divided by 2. And that should give us 2.6. 2.6 times 10 to the minus 5. So now we've got our concentrations over here, which is good, because now we can use that. So now let's put that into our expression. So it was Kc equals the products, the concentration of the products, which is 2.6 times 10 to the minus 5, divided by 3.1 times 10 to the minus 3, and that is for carbon monoxide. And we can see over here that there's no superscript here. And for H2, it would be 2.4 times 10 to the minus 2 squared. Remember, we had a superscript over here, so we need to have a superscript over here. Now, putting that into our calculator, we would get the answer of 14.56. It would be recommended that we leave everything we leave our answers and everything that we write to the same number of decimal places in the original question. So over here it's 2, 2, 2, so we should have it as 2. Now, to figure out the units, we know that the units for concentration is mole per decimeter cubed. So if we replace these with moles per decimeter cubed times mole per decimeter cubed. All I've done here, by the way, just in case you don't get it, is that I have removed the units, because usually I would write 2.6 times 10 to the minus 5 mole per decimeter cubed over 3.10 times 10 to the minus 3 moles per decimeter cubed times yada yada yada. All I've done is just put them into a separate equation. We could see that as we've got 1 mole per deciliter cubed here and 1 mole per deciliter cubed here, we could just cancel them out. If you do maths, you can prove that by saying, yeah, let's not go into that. And that will leave us with mole per deciliter cubed, but we need to flip it over, so it will be mole minus 1 deciliter cubed. Okay, if you need any more help with that, please browse through my other videos where there should be one explaining how to actually get this. Now, for the next question, which is very popular, this is a January 2006 paper. I should have said that this is January 2003, January 2006. So, the preparation of hydrogen iodide for hydrogen and iodine gases is a reversible reaction which requires equilibrium. This should tell you the subject which you need to focus on. So, the first thing, write the expression for this equilibrium. That means you've got to write it for this equation. So that would be Kc equals Hi, concentration of Hi squared over H2 I2. And that will give you the mark. The next question is that the students mixed together 0.3 moles of H2 with 0.2 moles of I2 at the start. And that's very important because this is the type of question that requires you to figure out how much moles has been used up. And there we go. Okay, we even got a table. They even gave us a nicely laid out table. So, what we've got to do is to complete the table to show the amounts in the equilibrium mixture. So, at the start, we've had 0.3 moles of H2, 0.2 moles of I2, and obviously 0 moles of HI. Because at the start of the reaction, we haven't made any of it. Okay, we don't put in HI at the start of the reaction. We want to make it. So, at equilibrium, 0.14 moles of H2 was present. So we can write that there. Because at equilibrium, that amount of moles was present. So, how many moles was used up? A simple calculation, 0.3 minus 0.14 will give us 0.16. So 0.16 moles of hydrogen gas has been used up. So, as you can see in the reaction over here, that this is a 1-to-1. So whatever amount of moles has been used up here in H2, the same number of moles must have been used up in I2. So 0.16 moles has been used up. So 0.2 minus 0.16 will make 0.04 moles. And over here, obviously, this is what we're making. So we have 2 times the amount of moles which has been used up here be made here. So instead of 0.16 moles being made, 0.32 moles have been made, because you can see over here that for every 2 moles, actually that's a rubbish sentence, we can see that 2 moles of HI has been made for every mole of H2 and I2 being used. Pardon me. Sorry about that. Okay, so 0.32 moles has been made. So that's that question done. And that question is 3 marks, I should think. 2 marks, okay. So, calculate Kc to the appropriate number of significant figures. Now, you would fall into the trap if you put all the numbers in equilibrium into the expression. But you need to be aware that what we've got here are moles and not the concentration. Because remember, Kc is measured from the concentration, from the proportion of concentrations of the reagents and the products. So we don't have a volume here. So how do we know what volume to put it in? If you want to hear this explanation of why we don't actually need the volume in this case, please listen on. If you don't want to and just want to know that if we don't have the volume, it is safe to assume at most times to just put these numbers into the equation, into the expression, then please skip forward, I don't know, 1 minute, 2 minutes, I don't know, one of them. So, as you can see here, to get the volume of these moles, we have to do N divided by V. So, we don't know what the volume is, so we just leave it as V. Now let's put this in the equation. Kc equals, and it's going to be a very big one, by the way. It's going to be that big because my handwriting is quite big, as you probably noticed. So it's going to be the products, which is 0.32 moles divided by V. Okay, so that's the concentration of the products over, squared, sorry. Yeah, 2 moles, yep. So it's squared over 0.14 divided by V to get the concentration of hydrogen gas times 0.04 divided by V, which is the concentration of the iodine gas. Now, if you do maths, we can see that we've got 2 V's here. If you can't see it, I can literally write what I just wrote there as that. So as you can see, there are 2 V's here and there's 2 V's there. So we can cross them out. And if you do maths, you'll be able to, especially C3, you'll be able to notice this, as there are 2 V's at the top, 2 V's at the bottom. That means we can cross them out. So it would look like this: 0.32 squared over 0.14 times 0.04. Okay? And welcome back, those who skipped the 30 seconds. So let's get rid of that. If we figure this out, if we just do this in our calculator, we would be able, we would get 18.28571429. But as you can see, it is in 2 decimal places, but you could just write 18. Wait, hold on. It says appropriate number of significant figures. I'll say 2 significant figures is kind of appropriate. So we have 18 to 2 significant figures, and the units will be mole per decimeter cubed over mole per decimeter cubed times mole per decimeter cubed. By the way, this is squared because over here we've got 2 of them, 2 of 0.32s, so we need to have 2 of mole per decimeter cubed. So we've got 2 of them here, and we've got 2 of them here, so we can cancel them all out, and there are no units. You need to write no units, otherwise you will not get that mark. And that is it. I know that was pretty long, but that is it for calculations using KC.